This lesson is on continuity. This is section 1-4. So what exactly do we mean by continuity? What would be a good definition? Well, a simple definition would be that if you traced the graph, your pencil or pen would never have to leave. So you could trace the graph and you never have to lift your pencil up. Now, with this graph here, if I trace this graph, all of a sudden I got to lift the pencil up and move down here and continuing. So this would represent a discontinuity, whereas the one on the left would be a continuous function. So let's look at a more formal definition of continuity, however. In order for a function to be continuous, the following three conditions must be met, okay? All right, the first is that the function is defined at x equals c. So we're trying to see whether or not this function is continuous at the point x equals c. So it has to be defined there. The limit of the function as x approaches c from both sides has to exist. So the function has to be defined, the limit has to exist, and the limit has to equal the value of the function at that point. All right? So function is defined, the limit exists as x approaches c, and the limit as x approaches c is equal to the function value at c. So what are the types of discontinuities? Well, there are three basic types. There's a removable discontinuity, or a hole, a discontinuity due to vertical asymptote, and a jump discontinuity. So let's see what each of those looks like. A removable or hole discontinuity is shown in this graph here, all right? So at this point here, the function does not exist, okay? That's the reason we have the hole there, okay? So that's a removable or hole discontinuity. Due to a vertical asymptote here, notice on this function here, we have a vertical asymptote, and on the left of the vertical asymptote we're going up, and on the right of the vertical asymptote we're going down, but there's a discontinuity between those 2 points. So that's a discontinuity due to a vertical asymptote. Then the last one is a jump discontinuity. Notice the function is coming along here and going up here, then all of a sudden we jump to up here and then go down. So this is referred to as a jump discontinuity. All right, so let's look at an example. So for each of these, identify the x value and type of each discontinuity. Well, the first one here is we've got x squared minus 7x plus 10 over x squared plus 4x minus 12. Well, how are we going to figure out where this is discontinuous? So we're going to have to do something, we're going to have to factor it. And if we factor it, we end up with x minus 5 times x minus 2 on the top, x plus 6 times x minus 2 on the bottom. Now notice, we can cancel out the x minus 2. Well, we have removed it from the function. Therefore, we know there is a hole at x equals 2. Because if x equals 2, the denominator is going to be 0. So there's a hole, or a removable discontinuity at x equals 2. Now look at what we've got left. We've got x minus 5 over x plus 6. Well, x plus 6 is going to be 0 if x is equal to minus 6. So therefore, we have a vertical asymptote at x equals minus 6. So now let's look at the next one here. We've got f of x equals the square root of 3x minus 2. Where could there be a discontinuity there? That looks like a continuous function. And the answer is yes, it is continuous, but it's continuous on its domain. Why? Because x must be greater than or equal to 2/3. Because if x is less than 2/3, we end up with the square root of a negative number, which is invalid, so the function's not valid for values less than 2/3. So it is considered to be continuous, but only on its domain. So now let's look at this last function, this piecewise function, where we've got f of x is equal to x squared minus 2x plus 1 for x less than minus 1, and it's equal to x plus 2 for x greater than or equal to minus 1. Now the first thing we're going to have to do is see what happens at minus 1, okay? So if we plug in minus 1 in this first equation, I'm going to get minus 1 squared, which is 1. Minus 2 times minus 1 is going to be plus 2. So I've got 1 plus 2 plus 1. So that comes out equaling 4. All right? The second one, if I plug in minus 1, what do I get? I get minus 1 plus 2. I get 1. So there's a discontinuity at minus 1. At this function, as they're approaching minus 1 from the left-hand side, is equal to 4, but as you're approaching minus 1 from the right-hand side, it's equal to 1, so therefore this is considered to be a jump discontinuity at x equals minus 1. Now let's look at restrictions on the domain. We talked about being continuous on the domain. Well, what if we have a particular restriction? Now there's two types of restrictions. We could have a restriction because of the denominator or a restriction because of radicals. The denominator basically means we've got a restriction. The denominator cannot be equal to 0. So if the denominator cannot be equal to 0, in this particular function of x minus 5 over x plus 1, we know that x cannot equal minus 1. So that's our restriction in this case. So x can be anything except it cannot be minus 1. Now, let's look at the next example where we've got a radical. So we got the square root of 7x plus 3. Well, we know that underneath the radical cannot be negative. So 7x plus 3 must be greater than or equal to 0, or solving that, x must be greater than or equal to minus 3/7. So that's our restriction. X cannot be less than minus 3/7. It must be greater than or equal to minus 3/7. So that is our restriction in that case when it comes to radicals. Well, now let's look at something referred to as the intermediate value theorem for continuous functions. So let's look at our example here, and then let's look at the description here. So we've got a function f shown in this graph, all right? If f is continuous from a to b, so from a to b, this is continuous, okay? There's no holes, there's no jumps, there's no asymptotes. So it's a continuous function from a to b. Then every value between f of a and f of b exists at some interval a to b. So every y value here is going to exist for an x value in this area here. Now, you might say, well, isn't that obvious? Well, it sort of is, but it does have value, and let me show you an example where you can use this intermediate value theorem to good use. Here's an example. We want to use the intermediate value theorem, and I've abbreviated it here by IVT, to answer the following questions about the continuous function f of x is equal to 2x cubed minus x minus 5, all right? So we're told this is continuous, all right? So we're told that function is continuous. Well, first of all, they want to know what is f of 1, what is f of 2, and does the function have a 0? Well, if I plug in x equals 1, we'll find that f of 1 is equal to minus 4. So if I plug in minus 1 for x cubed, cubed minus 1, plus 1 for x cubed. If I plug in 1 for x here and I figure out what the answer is, I come out with a value of minus 4. So f of 1 is equal to minus 4. Now, the second question, what is f of 2? So if I plug in 2 for x, what do I get? I get f of 2 is equal to plus 9. okay? So f of 1 is equal to minus 4, f of 2 is equal to plus 9. Now, the question is, does the function have a 0? The answer is yes, it does have a 0, all right? And why do we know that? Because of the intermediate value theorem. Notice we said this function was continuous. We know that at x equals 1, y is equal to minus 4. At x equals 2, y is equal to plus 9. So therefore, somewhere between 1 and 2, it has to equal 0. So here's a case where we use the intermediate value theorem, and we could determine whether or not a function had a 0.